Welcome, everyone. I'm Veronica. I'm the president of the UFRJ Student Chapter. And this is our annual lecture we hold every year about one of the subjects of the COPRI. For those of you who don't know, COPRI is one of the institutes of the American Society of Civil Engineers. Is the Coast, Oceans, Ports, and Rivers Institute. And UFRJ, it's a COPRI, it's a student chapter of this institute. We are from Federal University of Rio de Janeiro, Brazil, and we are a group of graduate students from the related areas of the COPRI, the coasts, oceans, ports, and rivers. Our team is have members from the master's and doctoral degree students from different areas of different backgrounds, academic backgrounds, professional backgrounds. We have a good range of professions and different research areas. So with a good exchange with between the members. We start at the Ocean Engineer and Civil Engineer programs of the UFRJ. And now we have students from many different graduate programs. So we are a group open to any graduate students at UFRJ that shares the interest in the areas of the COPRI and the activities we developed, which are activities that seek to promote increase the knowledge and practice of related disciplines applied to the coastal, oceans, ports, and rivers areas, to connect the university, society, in industry in discussions, and promote professional development. Our activities, between our activities, we have workshops, we have courses, lectures, where we try to maintain a balance between lectures that we want to share widely knowledge, such as the lectures of today, and activities that for academic, technical, and professional development for our members. We also have technical field trips, participation in conference, and virtual content on our YouTube channel. And to be a member of the student chapter, to be a member of our group, you need to be a UFRJ graduate student of any program and share these interests for our activities. And you also have to be an ACCE members and a COPRI member, which is a free membership for students, and participate in the regular meetings and the activities. If you have the curiosity to know more about the chapter, how is to be a member, or you have the interest to be a member, please contact us and any of our social media that are these on the screen, and through our email. So that's our short introduction about us, about who we are and what we do. And now let's go to the main goal of today, that's the lecture, the reason you are all here today. This year's annual lecture has a theme of rivers, and the lecture will be an Evolving Mult-Sector Geospatial Gateway for River Basin Management. Our guest is Professor Jeffrey Richey. He is a professor at the University of Washington, is also a visiting professor at São Paulo University, a member of the Brazilian Academy of Sciences, and fellow at the American Geophysical Union. Professor Richey has many years of experience in working with water resources. And Professor, we are very pleased to have you here today to share some of this experience with us. And before I give you the floor to start the lecture, I have just two things I wanted to say to the public. We have this Q&A section at the end. You are free to send your question anytime in the chat. We have people from the UFRJ COPRI here that will be selecting, noting the questions to ask at the end. But if you prefer, you can also, at the end, open your microphone and your camera and ask the question directly. We send instructions again to the presentation at the end in the chat. So I think that's out. And please turn off your camera and your microphone during the lecture. You can open them at the end if you want to engage at the Q&A section. I think this is for me. Professor, you are free to start.
Ok, muito obrigado, Verônica. Que bom para voltar com todo mundo aqui. Estou com tantas saudades desse grupo COPRI, o Rio de Janeiro. Desculpe, minha português agora faz 1 ano e meio desde a última vez que falava muito, de março de ano passado. Obviamente, não deu para voltar desde aquela época. As Veronica just said, the first place, I'm honored to be here after listening to Professor Joanna last year on the subject of ports. And so now we'll be moving a little bit more into rivers. That said, what I'm looking at today is a little bit more of a broad interpretation of rivers, how rivers are a central part of a river basin. And we're looking at the overall issues of how to manage such water resources, but not just by us professionals, but by a broader audience with those people who ultimately are really impacted. So my objectives for today, first of all, is to go through a rationale and a strategy for what we call a dynamic information framework to engage resource agencies at different countries at different levels of development around the world, and where that came from and some of the examples. This work has been developed through collaborations and participation in different World Bank projects. The World Bank is an instrumental player in resource development, obviously, in much of the world, especially the developing world. So it provides a really unique aspect for how to think about river basin management and bringing resources to bear. So after a brief introduction on where that's coming from, I will go through a series of some of the case studies of what we've done over the last 10, 15, a little bit more years, and especially the lessons that we've learned. So as I go through the case studies, it's less about what exactly we did and a little bit more about how the setup goes. Now, a central underlying theme in all this, which took a long time for us to come to grips with, is how do you actually manage all the information required to actually do an integrated analysis of a large scale drainage basin? Lots of different pieces, and pretty soon business as usual will get swamped out. So I've been very excited to start learning lessons and moving towards the world of big data and open science and kinds of problems. And so that will be an emerging theme as I go through this. Then the third part of the presentation will be looking at measurements that our research group has made on the lower Amazon River with a focus on some of the issues that have come out in our earlier case studies, but really looking at river specific problems, but much how to handle large streams of lots of information and how can we possibly deal with it. I'm just what we like to kid and say, just an old river rat. And for us, it's been quite a learning experience. And then just a brief thought about where we might go into the future and really take advantage of some of the really exciting technologies and capabilities that are coming out from different places around the world. But the common theme of how can everybody work together to get to a bigger spot in our ability to manage ultimately water resources. Key aspect, of course, is that rivers are the absolute central part of how you think about the overall water resource issue. So we're not exactly the first group between those of us in this room here today to think about how to manage water resources. This is Angkor Wat in Cambodia with a long history of water resources. Go back, the first kind of knowledge about water resource management goes back to the Mesopotamian civilization thousands of years ago on the Tigris and Euphrates rivers. And then through these various other evolutions from the Indus, the ancient Egyptians, Mayans, Chinese, Greeks, Romans, Aztecs, Incas, and truly extraordinary stuff. And even Rio de Janeiro was an integral part of this history with the Arcos de Lapa aqueduct, which actually goes a lot back further than I thought. So Rio is part of a long history of resource management. But all these issues start becoming more real now. As we all know, global water resources under stresses from multiple different sources. This is a map produced from the GRACE satellite of total water storage, which is the total amount of water from the atmosphere down to the core of the earth down into groundwater. So Riddell and company went through and looked at where do you have sheet loss, where do you have depletion in groundwater, what areas are increasing, what areas are decreasing, all of which are add up to vast changes in global water resources. So the challenge is, how can we as a community, everybody listening in here, take all that kind of information and bring it to bear with agencies that are nominally responsible for mobilizing this information. So we can think about the overall river basin resource issues as sort of a sandwich of different problems. First of all is managing water demand. Increases in population and agriculture exacerbated by climate change produces an overall huge stress on water. The change in land use, which is a major issue in much of the world, is very change driven. How do you optimize resources? We're going to see ever increasing progressive extremes, flood situations, drought situations. Prediction is fundamental for the longer term as well as an immediate disaster. Are we going to get a major storm in 15 minutes that's going to really impact a village? So how do we dial this stuff together? And then how is a knowledge chain established? This is my colleague, Eric, in the World Bank, when we're at a trip in Mozambique, which we'll see in a minute, talking with the local population about what are the major issues that these people are concerned with. For example, for these farmers along the Zambezi River, if they knew in 3 weeks out, if it's going to be a wetter period or a drier period, then they would know whether or not to plant higher value, higher risk crops or lower value, lower risk crops. They're acutely aware of these trade-offs. How do we as a whole get them that information? So with Eric and others, we work with the Global Environment Facility and different World Bank projects to look at how do you construct basically a system for what's ultimately decision support, where you can go, so we're driven by applications across time and space scales. What are the resource requirements that a particular area needs? How do you mobilize the information, that crosses into actual actionable information? So the basic strategy was to look at Earth system modeling and then how to dial that through a policy interface to produce usable results. So the reason for the Earth system modeling is that's a good way to go from the knowledge that we in the earth science world get and bring it into some aspect of utility. So there are several important caveats that are not caveats, challenges to be met. One is that information has to be sufficiently precise to be of both of utility for short and long range planning. Some grand hand waving thing at too broad a scale does nobody any good. It's important to have not only the best information, but the best possible open information to be able to derive this from. An awful lot of information around the world and data is hidden in behind locked doors and in file cabinets and so forth, and it makes it untrustworthy to be able to get to it. Your capability has to be strong enough, but to produce the right answers, but the execution has to be done without somebody having gotten a PhD from UFRJ in computer modeling. So how can you make the interfaces sufficiently friendly yet powerful enough to be of use? It's useful to be visually compelling for multiple levels of decision makers. If you can put up all the charts and tables and spreadsheets and all that kind of stuff you want, but if that information isn't transferred to some way that the Minister of the Environment of the sector of agricultural resource management, whatever, can't see or doesn't, then it's no good. So can we take that information and make it visual? That, of course, makes for very interesting problems in just workflows, data processing, to go from all these individual bits to something that somebody can just look at and say, oh, I see what's going on. And finally, it's critical to engage and be led by the local players. If you don't have local player input, nobody's going to pay any attention, and it goes beyond that. You have to have the local players who are going to take over the enterprise to be the local champions, all of which is fine, but much of this is easier said than done. So let's see where this all goes. So the hydrologic cycle is, of course, the sort of the fundamental underpinning to all this, where if we can keep track of what's the level of rainfall that falls on the land surface, produces evapotranspiration, runoff into the rivers, ultimately makes its way downhill, and ultimately makes it to the ocean. We can keep track of all the processes on top of that in a first principles basis. Then we have a chance of being able to understand how change might eventually occur. Of course, this does tap into the multiple aspects of the earth sciences: hydrology, geology, climatology, and so forth, which makes it fun to how do you actually pull all this stuff together. So the basic formula that we're looking at is what is the change in the total surface water, which is preset minus ET minus runoff, plus or minus snow and soil moisture. Simple enough, right? Just to evaluate those terms. Simple, quote unquote. And then that gives the total change in water storage on the land surface is not only the surface water component, but groundwater. Clearly, groundwater is certainly an emerging big scale issue right now, as groundwater around the world, the big aquifers, including in Brazil, are being depleted with questionable aspects of how these can be recharged. So taking that hydrology network framework, the strategy is to then represent that in geospatially explicit hydrology models. These tend to go from, there are multiple different ones that look at a coarser scale, how to represent the land surface at the order of 5 kilometers to 100 kilometers, which is where these things started, to a finer scale of representation that, say, 30 meters, or a scale of a Landsat pixel, that can pick up local variability, but the information requirements are that much greater. The model our group has been using is something called the variable infiltration capacity, but there's certainly many others that do the same sort of thing with certain sets of assumptions. The DHSVM is a high resolution, terrible name, distributed hydrology soil vegetation model. That now this is being, there are certainly various other ones of this general genre. So which model you use is important. It's the data requirements that go into these, that drive them, that becomes interesting, presents interesting challenges. What scales, how much information can you process? So the basic framework we've been looking at is to be able to get to the policies you want that have to do with how much soil moisture, what's happening with droughts and floods, changes in agricultural production, hydroelectricity, gas emissions. That to get there, we can look at the computational engine, these geospatial models. So this is an abstract from Vic cartoon in this case. And then how do you assemble the data modules for doing this? You need to have topography, which delineates the river basin boundaries, what the slope is, how the overall river networks are organized. Clearly need to know what kind of soils there are, how permeable or how hard packed. Use and biodiversity, tropical rainforests, savannas, deserts, whatever. Infrastructure is an inescapable component. Any more roads, dams, cities, and then put climate on top of it. Then so anytime you go to some place, you have to be able to take your best available information to produce these data layers that then feed into your model to produce your outcomes. Now, river basins typically don't follow political boundaries. Sad fact, but true, or a complicating fact. I don't know if it's sad. And so if the river basin stops at some boundary somewhere, makes it more complicated sometimes to actually get all the information you need. So anyway, if everything goes well, you can turn it on, feed the models, and get out the views of what's happening on your policy ends. So the way to look at organizing that information is we came up with the term dynamic information framework, simply to represent how dynamic all the information is, how that you're looking at information, not just data, and it's a framework that's ultimately flexible to look at all these things, topography, soils, land cover, and so forth. And then the process of organizing it, and where does that information comes from? Sensors, data archives, metadata, GIS, or system models, so forth, all this stuff. And so the challenge is, how do you hook all that together? Then the idea is, at that point, then you make yourself a time machine, basically. You can go back in time to see what things you used to look at, which gives you information about, or at least insight into what might happen in the future. So that's the overall sort of general strategy that we've been trying to work towards. Every project that comes along, we learn more equipment, or the information gets better. And sometimes it goes backward. The devil in the details in a lot of this. It's easy enough to make these nice little cartoons, but what's going to happen in real life? So that brings this little cartoon, if I could put in, speaking of that devil, so that awful lot of data, big data, and a lot of noise that goes with it. So I like this cartoon. It says, the professor to the student, don't worry, you don't have to start your code from scratch. You can reuse the software that the previous person of the project wrote several years ago. And the student, of whom many, of course, are on this call at the moment, are there instructions for how to use it? I doubt it. Is the code commented? Not likely. Where are the files? Who knows? The student rightfully recognizes this is going to be painful, isn't it? Just to scratch. And says the rather overly optimistic professor. So the issue for us students here is to work through all this, and how can we make this whole process a little bit less painful. So the overall issue comes up is that rapid advances in our ability to acquire and generate data have outpaced ability to extract knowledge from all this heterogeneous, massive stuff, which can lead to significant bottlenecks. This goes in every field of inquiry, not just in civil engineering or sciences. That is, data is getting too much for regular people to do something with. These comments from a recent talk by one of our colleagues at UW, Amanda Tan, and who's gotten very involved in the how do you organize large-scale information to deal with such environmental problems. So now I'm going to look at some of the case studies that we've done at different parts of the world, which has been a pretty fascinating experience. So the first call is in the Zambezi River Basin of East Africa, across 9 countries, where there is a global environment facility project called the Zambezi Valley Market-Led Smallholder Development Project. And our job was to start looking at baseline data on land use, biodiversity, and hydrology. Sort of the time frame of most of the work was in 2006, and various parts of went on for a while afterwards. Very challenging region to be in. So we did various expeditions out across the countryside here, getting water samples and water resource information from one of the local wells along the lower Zambezi in Mozambique here. We assembled our first of our dynamic information frameworks in what we called the Zambezi DIF, where the issues were how will change, looking at how will change in climate, resources, practice in the upper Zambezi impact what happens in the lower basin. How does the dam operations, something called the Cohorabasa, impact downstream flow and floodplain agriculture? Climate change projections, how will upstream practices impact the delta? Now, all this sounds kind of normal now, but that was actually in 2006, where people were starting to think about such issues. So assembled information on land cover, upstream flow, dam operations, downstream flow, and so forth, represented the results on an internet map server. Now, that turns out that the hydrology information, the river flow data, is virtually non-existent. There were several gauges that we were able to get data from for the VIC modeling effort, and certainly very little ground data of any sort on hydrology or local climatology and so forth. This is working with the Era Zambezi, which is essentially the ANA, Agência Nacional de Águas of Zambezi. Little side note, of course, is in Mozambique, Portuguese is the language spoken, but Mozambiques don't always understand when you use the gíria of Rio de Janeiro, for example, made for several funny exchanges. And some of the challenges in working that area, first of all, it's noted that that area was under major trauma through a civil war that lasted from 1977 to 1992. We were there, so the infrastructure was just back to being replaced. And so that's part of the reason why there was so little information available. How to go from big basins down to the smallholder agriculture in the specific little areas here was challenging. Resolution of the land cover data, climate forcing sparse, total lack of river data, certain amount of institutional resistance to data sharing. Funny story is we were at one of the resource agencies trying to find flow data when the people in charge said, well, I don't really have any. And I said, here, let's have a look. I had my laptop with a computer, with our very first try at a model of the basin. This fellow said, where did you get that? So transparency, things in silos, big issues. And then working with and transitioning the model code. There was a group there that did begin to pick it up and go to a second generation. So this is a fascinating first look. A next project was working with the Chinese Academy of Sciences on mainstreaming climate change adaptation in irrigated agriculture in the Huanghe, the 3H plain of Northeast China, which is the big breadbasket of China, and also one of the driest sections. a major $500 million loan was being discussed to put in irrigation, massive irrigation projects, when somebody asked, what happens if the climate changes and we don't have enough water to do that? Well, good question. And so that led to this World Bank GF project to think about that issue. So led by the Chinese Academy of Science group using the VIC model, hydrologic projections under different climate change scenarios were made. This just one, so changes in precip, ET, soil moisture, and runoff under different conditions. Jack up temperature by 5 degrees and reduce precip by 15 degrees relative to normal. So there's difference. And so we ran various versions of that outcome. Then the results were taken and say, okay, what happens with those climate changes? What's going to happen to crop yields? So a crop yield model called the Vegetation Interface Program was run and produced different estimates of what would happen in this case to maize and wheat under different CO2 and temperature controls or control ranges. So the challenges we faced out of that one were, first place, not so much. The Chinese Academy of Sciences, very, very competent individuals, to say the least. A lot of discussions about data sources. Are the data resolution at that point in time anyway fine enough to really address these problems? How do you get in and work with the regional jurisdictions with the outcomes? A project we've got quite involved is on the Mekong River Basin of Southeast Asia, where the Mekong starts way up here in China. Interestingly enough, Yangtze starts just 50 kilometers away and then goes off in that direction. So it comes down from China down through Burma, Laos, Thailand, Cambodia, and finally back out down into Vietnam. Very interesting feature here is the Tonle Sap Lake, the enormous lake that's home to the biggest freshwater fishery in the world, tremendous fish production that feeds vast amounts of the population of this region. Local fishermen, the rivers that comes down out of China into working its way down towards the Mekong Delta. This is the Mekong River Commission, which is the agency nominally in charge of evaluating the overall resource issues in the basin. They don't actually have any legal jurisdiction per se, but it's a very interesting advisory group. So big questions there. Will the combined dams, so the Chinese already have 6 dams in, plus climate change, and more dams are being planned on the lower river, have a significant impact on the flow regime and livelihood of the people along the Mekong. Many different players in this. We developed an application using the VIC modeling effort to try and look at some of the changes of, first of all, what's the natural cycle of the river flow, and then clouds up here. Our early days of visualization of seeing what happens in the lower part of the basin. Lots of conflicts between when it's dry in the lower basin, the countries there will say the Chinese are withholding water behind the reservoirs. So the Chinese will say, no, we're not, it's dry. So these are the kind of models that become really useful. What happens to the Tonle Sap is a huge issue, as dams are not only up in China, but being discussed down along this area. We then worked with the Mekong River Commission itself to develop a visual Mekong basin as a means to try and share information from the various technical sectors, the various stakeholders, into a broader audience. This project is still a little bit alive, but now there's so many other players and actions involved. It's a very complicated region. So we have the challenges we face there were the data issues and getting the code. Problem, as our graduate student in that earlier image said, that the code to run these models is generations of graduate students and very poorly documented and so forth. So trying to teach those in other countries how to use this stuff can be a problem. Geopolitics in the area is quite extreme. Geopolitics, of course, is a theme that runs through all these discussions of water resources. So elsewhere in Asia, moving into up into the Himalayas, into the country of Bhutan, which is a land of gross national happiness. Fascinating, absolutely fascinating country, tremendously steep terrain. The maximum speed limit on roads is something like 40 kilometers per hour. Any faster, you go flying off the road and fall 500 meters down the side here. Quite isolated from the rest of the world, but lots of hydro potential. So they end up being able to sell much of their electricity to India in particular. So in this case, they're very subject to even the marketplace for hydro is short term, what's going to happen in the next 15 minutes. So the ability to predict how much water flow you have to be able to generate how much electricity is really a fundamental component to their portfolio. That said, extremely mountainous country, very difficult to access anywhere to get data. So we're part of a program to develop this druk. Druk is the national symbol, essentially this stylized dragon sort of person. The airline is called Druk Air. So that's where that term comes from. To try and develop these kind of modeling frameworks across the country to address some of the resource interpolation issues. And a number of different agencies were involved. There really is something called the Gross National Happiness Commission. The Druk Green Power Corporation are the pretty powerful outfit responsible for the whole electric sector and these various other groups. Challenge is how to work across these to produce information of interest. So arranging information from the large-scale modeling efforts and the large-scale, smaller scale into topography, land cover, and so forth. Parts of both, actually in Zambezi and here, where biodiversity, where one of the colleagues in the group would do these extremely interesting landscape mapping transects to where the basic idea is if you could go out for 40 meters and see what biodiversity or plant vegetation was, you could come up with functional indices of broader extent. It was cool stuff. This symbol here is part of sort of Bhutan lore. It's an elephant, a monkey, a rabbit, and a bird. And the issue is trying to reach the fruit. No one of these guys, even the big elephant, can do it by himself. But if you form collaborations between everybody, then you can get to the your goal, the low-hanging fruit in this case. So finally developed, this is the VIC model across the country. Now, it's kind of a problem here in that very steep terrain. VIC at a spatial resolution of 5 kilometers goes from mountaintop to mountaintop. So it would include saying that, so here's monsoons coming on with all the bright lights. Can you apply a macro scale model like that to such a steep terrain? So because of that, we use the high resolution model in a few places with the problem of actually getting enough information to be able to do that. So the challenges we faced there was is the VIC scale versus local ultra steep topography suitable? Can you get enough information to run something like DHSVM? Interesting of trying to take the global databases that were used for producing the vegetation and soil covers as a vastly coarser scale than local information on soils, but that information wasn't really available. Off to a good start on training, but then the key students left and went to Australia for future training. So we're unable to continue. This is the early days of thinking about the cloud, and Bhutan didn't exactly have great bandwidth, but there was a distinct aversion to putting anything up in the cloud for broader data sharing. Then you have the problem of the computer locked into somebody's back office. And there, in spite of the discussion of collaborations, there was quite a lot of interagency competition and lack of local champion. The reason I'm going through these challenges is to understand what we could and couldn't do, but how can information sources in the future respond to being able to get around some of those kind of problems. Then we moved to the Aral Sea Basin in the 2010, 2011 timeframe. Aral Sea Basin is in Central Asia, made up of the upper countries, Afghanistan, Tajikistan, Kyrgyzstan, down into Uzbekistan, Kazakhstan, and so forth. With the bottom is the famous Aral Sea, which from 2000 has been getting drier and drier and drier and drier until it's almost disappearing. So back to the Soviet era of highly engineered water withdrawals for crops, and along the way, completely depleting the Aral Sea and the fisheries and the livelihoods that went with that. So there was a very interesting bank program called the Central Asia Energy and Water Development Program that started in sort of the 2010. It continued the idea of how do you adjudicate between regional energy and water security through enhanced regional cooperations. So to involve representatives of the 6 primary countries with some of the flashpoints along the way. So our job was to think about sort of the water movement, hydroelectric, total basin water, naturalized flow, runoff in this area, with the specific task of developing a first generation models from publicly available time series data and model platforms. So the Sir Darya is this river and the Amu Darya is the bottom one. And across these systems, get a better understanding of the energy and water source linkages, but especially to provoke dialogue and discussion between the different stakeholders. And so the whole point is really work towards a neutral and transparent platform. So at that level, that meant that we used globally available data and not local per se, because that was really what Uzbekistan might have, Kazakhstan would object to violently. And tried to be a catalyst for open and transparent discussions, but at the same time, not substitute or replace for all the other stuff going on in the region. So it was really quite a fascinating portfolio to look at. So the levels of data integration, so topography came from the SRTM shuttle radar topography mission, HydroSedge, down to a 3-second database for the Sir and the Amu Darya rivers. So again, we start up in the Tien Shan Mountains, head back down across these vast deserts. When I first saw this, I thought that this was a data mistake, but it's actually a sink in the middle. And so the river basins don't even actually go in there. Then the soil data layers, there are a number of, and these are the same sort of data layers that we used in the various other models, that global FAO, UNESCO, soil programs, and so forth, with assigned hydrology variables. But who knows how good those are? The MODIS data sets provide vegetation cover, climate forcings from the different globally available reanalysis products that have been used in multiple studies. then the river discharge from the Global Runoff Data Center, and we did get some local runoff data. Dam locations. It's kind of funny going through, we were able to find a number of the dams just by cruising on the web and putting it into Google Earth. First time we showed this at a bank meeting, somebody in the back said, "What is that? Looks like spying." Because at that time, which wasn't that long ago, the fact that you could do that was a bit of a surprise. And then we could look at the change in the total basin water storage using the GRACE satellite and dialing all that stuff together. Problem for calibrating and validating, there were only a couple stations for the Sir Darya and the Amu Darya that were that had viable data. More recently, after the end of that project, a graduate student at Washington State University has been using machine learning of different climatology and river data sets to try and improve the flow records. From the upstream area, which is more concise, got pretty good results, blue is observed. Whereas downstream, once you get down into here, it's really kind of a mess. So it's hard to figure out what's actually getting into the RLC. So another one of the VIC model runs, doing different climate scenarios from data ensembles. It was pretty interesting, but at least a beginning towards thinking about those sort of directions. So the challenges we had were rationalizing multiple and not always transparent data sets. Some countries were very enthusiastic about shared access. Others, especially some of the old guard guys, not so much. Language, installing code. And then another one of the things to deal with in our, as we think, the graduate student who did all the initial modeling work left and took, I wouldn't say he took the code with him, but it was impossible to figure out what exactly he had done, and he went on to a different life. And so another example of how important it is to have a legacy of code installation. Future, all this stuff there is to be determined, function of the geopolitics of the region, but this stuff was opening eyes. It was pretty interesting. Moving closer to Brazil, we worked with the Espírito Santo region north of Rio on as part of the Programa de Conservação de Recuperação da Cobertura, etc. Here, so a geospatial gateway, where the idea was to have the same sort of robust information framework with the models and the data all rationalized. Again, a great aspect of pulling all this information together is to be able that everything's in the same projections and time frames and time steps and all that. When they come from such different sources, isn't always the case. So three main questions. How does the weather, rainfall, heat, translate to soil moisture, ET, and ultimately runoff and discharge across the landscape with the different timescales? How would changes in land use affect that movement? How would changes in land use and water mobilize sediment? Some of the rivers near Vitória, when it rains really hard, you get tremendous sediments, the rivers stop flowing because there's so much sediment, then of course it all bursts. And so this was the overall gateway to the PCGAPS, the name of the system. So work through on this here, the strategies, river basin information, data to the models, weather to runoffs, and so forth, this logical sequence for producing outcomes. We looked at VIC at the state level for the primary rivers, and then at the Santa Maria de Vitória and Jucu, small rivers for higher resolution work using the DHS model. Data from mixed sources, SRTM, Embrapa, IEMA, Incapera, which is the GIS outfit essentially of Espírito Santo, but issues in getting to the climate. It's going to be interesting look at data assimilation from the local geobase and IEMAs, what happens when you move from high resolution to progressively coarser resolution. How does that change what the model is going to see? So into the outputs, the VIC model for the Linieres, Oladeras, Cachoeira, and so forth did okay within local constraints. And then on the DHSVM, where we only had a couple of years ultimately of decent data. So fast forwarding through various steps here, then here are different precipitation and temperature regimes from, so this is the preset and the runoff responses under condition 100%, 10% of precip, no change in temperature, and so forth. Down at the local level, what are the land use change considerations? So these are different combinations of eucalyptus, different levels of agriculture. What would you expect the river flow outcome to be under those conditions? So the challenge is the same of some data acquisition, cross-agency cooperation, but the biggest problem was actually finding an agency and individuals dedicated to taking it over and keeping and embracing using the overall systems. The final of the series, we started several years ago in Nicaragua on dynamic information for climate smart landscapes and El Nino preparedness in a region that really gets hammered by volcanoes and hurricanes and earthquakes and so forth. So by now, so the information availabilities are increasing, which gets pretty interesting. One of the rationalizing the soil order from the FAO type soil maps with what's available in Nicaragua from the sources there, land cover maps. One of the more interesting evolutions at that point, a rainfall data set called CHIRPS, blanking out what it stands for now, which produces precip and aggregated over time at 5-kilometer resolution. So this becomes a significant improvement over the big reanalysis type products, especially for a geographically diverse region such as Nicaragua. We're beginning to make progress on the ability to compute observed flow versus simulated flow and how to proceed on that. But then the challenges are that we had multiple scaling, really good base for trainees, people really starting to engage in it. Official resistance to working in the cloud was that apparently it was a governmental strategy not to permit cloud access to international sources. With the overall situation there is with the current government situation, everything is pretty much on hold for who knows how long. Okay, so you've been very patient. Thank you for sitting with me through the sort of broader drainage basin issues that nominally come to focus on the river part, rivers, but now let's go down into the rivers themselves and some of the more advanced techniques that we can look at. Clearly, this is the Amazon River with a boto, not a boto rosa, but a regular porpoise jumping. So a group of us based at Sena Piracicaba, in Macapá, Belém, São José dos Campos, and so forth, had been working on in a project called Trocas, starting in 2013, and then phase 2 is ongoing, which is called looking at the net ecosystem exchange of the lower Amazon River from land to the ocean and atmosphere. The basic strategy is net ecosystem exchange is defined as the change in the concentration of CO2, dissolved in the water, as it moves downstream through net advection, river flow, as a product of concentration and discharge, plus the things that go on in the river, respiration and primary production, and outgassing. So the idea is if we can track all that stuff, we get a sense of what the CO2 dynamics are driven by. A key point here is that the CO2 outgassing from the Amazon River itself and surrounding waters is much greater than anyone thought and affects the overall carbon balance of the Amazon. The strategy has been to basically drive up and down the lower Amazon River in a series of, at this point, 8 expeditions on this wonderful boat called the Mirage. The Mirage is equipped with very, very nice laboratory setup, equipment, great captain who really knows the water. And so we go off on these trips. Right, so one of the key measurement sets we get is what's called is continuous data, underway data. And so everywhere we go over the hundreds of kilometers, take this mesh of tubing with Alini and Vanya here to suck water up and pass it through a series of instruments and make the underway measurements. So it's great to be able to do that because a bottle of water at the surface or halfway down somewhere in this vastly heterogeneous and dynamic environment is, what are you going to do with that? But if you drive along and you can see, quote unquote, what the concentration changes are, you can start figuring out to a much better degree what's going on. So the water gets pumped through a so-called equilibrator here and passes through this thing called an exosonde, which could make real-time measurements every second of dissolved CO2, oxygen temperature, turbidity, and chlorophyll, which we can combine with flow measurements from the so-called ADCP, and then using a fancy instrument here called a Picaro, measure not only the concentrations, but the stable isotope composition of the CO2 and the methane as you go along. It's kind of amazing to think that you can have a mass spectrometer on an Amazon riverboat making measurements every few seconds. When you stop and think about it, okay, every few seconds of measurements times however many thousands of kilometers we've gone, that makes an awful lot of data points, a little bit beyond the average Excel spreadsheet. So basically, we had to work towards this grand challenge. What do we do with all this stuff? And so at that point, even us river guys think, okay, let's think more broadly and back to this overall theme of as data gets progressively greater in volume, becomes big data. And also it's not necessarily clean data. There were holes in the instrument stopped and there was a voltage spike and all that. So it's not as if it's some nice smooth sequence. So we said, okay, let's just go for it and do a more contemporary overall data processing environment. So this is a web page, but one that's based in GitHub with the various components to it. Nothing fancy yet, but that's the point. So overall, our challenge is how do we develop a workflow to take all that sophisticated data from those instruments using, based on Python, which is a interpreted high-level general purpose programming language, working with GitHub for version control. So back to that poor graduate student who's wondering where to find anything, GitHub would definitely help you. And Jupyter Notebooks is a way to write code on a web browser that somebody can just go in. So all these kind of open science, being able to get around on things would get away from an awful lot of those problems that we encountered over the course of all those various individual studies and examples. So processing could go into that. And then on this case, the Heroku cloud platform, which allows multiple things to be done. This work was led by Emilio Mayorga at the UW. So much thanks to Emilio. He was not only a computer guy, but was a graduate student in our early days at the Amazon, and so knows what what's in a bottle of water issues actually are. And so this is the overall summary of the workflow we ended up developing. So the top level structure in the cloud, and at this point in the Google Drive, historical data and GPS tracks, hydrology records, and all this various stuff, individual chemical measurements, pictures. Now let's focus a bit here on the underway data component, which is what we need to look at. So this has the structure for each one of the individual cruises along here. So that ends up being about 1,200 individual sensor files with roughly 100 million individual observations with the metadata and stuff that comes out from doing that. So clearly one has to think pretty hard about, okay, what are we going to do with that? So the overall stream set, then we go from that underway data into what's been stored there into a data browser, which is basically a Python-based data exploration dashboard Emilio developed using these Holoviz Python packages on the Heroku Cloud platform for the team access. Then Emilio developed a set of Jupyter notebooks for processing the raw data from each sensor into standardized, nice, tidy data, all aggregated, everything's in the right structure. I mean, believe me, getting somebody's handheld GPS to sync with the exoson timings and so forth takes a while, and where all the missing data issues are and all that. But the beauty of doing this is, and once it's in this cloud optimized format, various code here, is then anytime something comes up, we updating the data or fixing a problem or whatever, boink, all you have to do is just dash it back through, or anybody from anywhere else can actually do that. So then there's the GitHub, which is the storing reserve for the browsers, I mean, for the Jupyter notebooks, and all the code then is openly available here. So finally, once this all gets dialed through, then you produce 1 minute bin analysis data set that can go into the Heroku, and then goes into this other folder called integrated, which is not exactly an original name, I'll admit, but gets to the point. Then ultimately you can move to the Amazon AWS S3 cloud storage and pens you into the big data platform stuff. And this all sounds confusing, and it's taken me a while to understand what Emilio's doing, but the logic of doing all this is really nice, and we can really start getting to being able to do useful stuff with all this. And so just one quick example of one of the sensor tracks that comes out, in this case for the dissolved CO2 from the Lycor for the cruises 1 through 8. So you can see that the cruises 1 through 4 were from Macapá up to Óbidos and back to Macapá. And the color intensities indicate where what is going on. Cruises 5 through 8 went from Macapá down to the mouth, back around in these areas. Then they show the frequency diagrams of the concentrations at different densities. You can go in the way Emilio has it set up and pull out, adjust scales, see what's going on. So it's just extraordinarily useful and powerful way of being able to compile all that, all the underway type data. This is from an early processing, not before Emilio really got things organized here, but the kinds of fun, colorful things. This is just from cruise 1, and it has a bunch of holes in it, and it's done by an earlier graduate student. But just the power of visualizing. So here's the low concentrations going CO2s, the cruise goes along, into concentrations of high. And so you look at this, and then, gee, it's on Google Earth, and oh, wait, I see. There's a lake on the side, or a Varzea. Oh, here's the mouth of the Tapajós coming in. Oh, there's the low water from the Tapajós coming. Okay, now we're going to go down. And I'm really excited about taking the Emilio's products and putting it back through some of this kind of visualization schema. So now that we have all that data, we've got to figure out what to do with it. And this is where Monica and the team at UFRJ will really comes in. So developing the CISPAIA modeling environment, which is the combined hydrodynamic and working towards putting this geochemistry stuff into it, will then give us presumably lots of insight into what's controlling that evolution of the parcel of water from upstream down until it gets out into the ocean and all its dynamic properties that occur along the way. Here's from an earlier iteration from Lourdes on the temporal evolution of tracers from upstream to down, and then it's oxygen from upstream to down. We go and look at and the field measurements. This actually, even this early iteration, did surprisingly well. So that's the kind of direction of thinking about river basins from the mountaintop down to the river, and then what's the evolution of and dynamics as you move along. So moving to the thinking about things that could be done in the future is really pretty darn exciting. So now there's starting to be just brand new data capabilities coming out. Outfit called AWARE is basically takes ground stations and various multiple satellite estimates and puts out and computes 9 kilometer by 9 kilometer contiguous pixels of rainfall and climatology, essentially creating 1.9 million virtual weather stations around the world. Think about the power of taking that kind of information and dialing it into a high resolution hydrology model to produce outflows. AWARES is just starting to been pushed by the World Bank and is really starting to make some impacts on computations or maps of economic resilience and so forth. But I'm excited about what can be done with dialing that into our river basin stuff. There's another outfit, in this case called Radiant.Earth, which is geospatial training data where they're basically taking machine learning. So if you dial in multiple sources of information, like the graduate student did for the Arrow, you can extract much more information about what the land surfaces look like. We're starting to think about how to do this even as part of our TROCUS project. But this kind of new direction, and then if you can organize it in these powerful information flow, and then think about open science, open source, really makes a difference. So basically, in summary, issues of concern are biodiversity, carbon, all that stuff are intrinsically linked in the scaled world. Subnote here about where mass is conserved is, I didn't really make a point of this earlier, but it's actually quite important because otherwise computations that go along and say this amount's going to be here and that amount there, if it's not, if mass isn't conserved, then you don't know what you're talking about. One thing that's always been said, data from multiple sources can serve to just confuse, but it actually a better way to think about it, constrain on problems. Embedded models that couple information sectors can bring data to life, as long as you have all the tools in gear. You can capable of evaluating multiple options and scenarios. It's like, what if, but what happens if the rainfall and the Madeira and the land use combined means there's less or more sediment coming out. But that all said, you have to convey this information in an accessible and compelling format to multiple audiences. So certainly these are information things. So here we are at the end of TROCUS 7 cruise, embrace moving to an open science with a new mindset and new open source tools about how to process all this river basin, river, and broader information. So I hope that by the time we do this next year, we can all be back in Rio de Janeiro having a caipirinha or two along the beaches. Obrigado pela sua atenção.
Thank you, Professor. Thank you for the lecture. We hope to be able to be together in the next year, in the next lectures. Now we are going to start the Q&A section. João is gonna coordinate this, so let's begin.
Whoa, first I want to say thank you, Professor Jeffrey, for this amazing technical explanation of water resource modeling. It's the first time I see this large and small scale modeling with this amazing smart researching with this computing modeling visualization. That's really very rich presentation, of course. And now I want to invite all our people that is watching for explain the answer for that question. And I have one question from Monica, and this is about there are so many variables used in modeling with VIC. She wants to know how is there an idea of the order of magnitude of the uncertainties of the results?
Boa pergunta. I think it's fair. To me, there are several big problems in it. A first order problem is, they're the obvious things. How good is your rainfall data? The beauty of rivers, of course, is that that's an absolute measurement. Mm-hmm. Minor problem, which isn't so minor in much of the world, river gauging stations are disappearing. And yes, there are some satellite things coming along nominally to help. But let's say for the moment that the river value is absolute. Then the rainfall measurements can have a really heavy rainfall in Ipanema and nothing in Copacabana. So what do you do with that sort of stuff? But in theory, you should be able to resolve some of that. I think the biggest problems for me are in the description of the soils, because you need to know what the soil infiltration rate is. Clearly, sand has a different infiltration than concrete. But soil data at that level is really, really tough. And so what ends up happening is that a lot of the calibration that goes on in VIC is actually done around the soil parameters. Yeah. So, what's the depth of the actual soil, what's the densities and so forth. So whether you want to call that calibration validation or inverse modeling is kind of an interesting call.
Yeah, definitely is a big challenge. There's many different layers. If you have no data from the soil layers, how you can really precise your runoff and even your other coefficients from your calculation. But that's amazing presentation, as we can see from the modeling, the animations. I also have a question. I'm very curious to know if there is any application of this modeling to help farmers to predict the right moment for cropping, and also to help them to prevent from droughts if they will lose or not the farm. As for example, we had a fire in the Pantanal, so this is in somehow will disturb the water cycle, that will have less rainfall in some area, but far from Pantanal, I think. So is there any application that you have already experienced on this kind of study?
So the question part was, can we anticipate the floods and fires and so forth?
All right.
Yeah, that's why the better we can do on all these driving variables. So think of the different static layers. But then what happens? The soil isn't going to change over the period of time we're interested in. But the more you can get into the ability to understand, especially I think the rainfall. That's why that AWARES thing is particularly exciting. That you can, if you can develop a history of the immediate history, then you can get a better idea of droughts and floods and potential. Even back to in the old days, back when we were doing the Mekong with that coarser information, all of a sudden a big flood came along that really surprised everybody. There hadn't been any typhoon or anything like that, as there often is in that area. And people say, where'd that come from? Onde veio isso? And turned out, when you went back and looked at the overall modeling, that there'd been a period of fairly sustained rainfall in sort of the mid-upper basin, enough to really saturate the soils, but below the threshold anybody got excited about it, until all of a sudden it was exceeded, and then the big flood came out. So I think the more you could make these kind of models absolutely operational would really help in being able to look for anticipate droughts and floods and so forth, and fires. What's the flammability threshold of a region?
Well, thank you for the answer, Professor Jeffrey. We didn't have many questions, so I want to invite our colleagues and all the telespectators to make some put your answers here. This is a good moment to enjoy Professor Jeffrey. That's a brilliant researcher, brilliant specialist on water management and modeling. So yes, guys, feel free to open your microphone and or video camera and put your questions on.
Tudo foi tão claro que não tem pergunta mais?
Professor
Jeff.
Paulo.
Olá, Paulo.
Tudo bem?
Tudo em cima.
Muito
Aqui
bom
não
vê-lo
opera.
aí. A última vez que eu te encontrei foi no seu aniversário.
É.
E a última vez que você esteve no Rio foi num jantar com a gente.
É. Última vez.
É. Muito bom. Saudades também aqui de vocês.
Igualmente, pelo amor de Deus.
É. Parabéns aí. Gostei demais da palestra. Super bom. Muito bom. É bom rever esses conceitos do DIF e ver que isso aí é uma luta grande para conseguir implementar isso. Necessita uma organização que normalmente aqui nos países a gente não costuma ter, mas seria ótimo se conseguíssemos implementar algo como o DIF.
Espero que
Muito
sim.
bom.
Não, é bem viável. Eu vejo seu grupo lá, que é fundamental para o futuro dessa tipo de coisa.
Vamos ver, a Mônica está aí finalizando os trabalhos da modelagem geométrica do Amazonas e vamos ver, essa semana que vem já vamos rodar o modelo, vamos ver.
Que bom, estou animado para ver tudo isso.
Você falou muito na dificuldade, né, da aquisição de dados e é realmente um desafio muito grande, né, como eu mostrei ainda num seminário há uma semana atrás aqui para o pessoal da engenharia costeira, e realmente it's a big challenge você conseguir não só coletar esses dados, preencher as lacunas, né, como também equalizar tudo para a mesma referência de nível, para a mesma referência espacial, que é um outro grande desafio, né? E não só espacial, como temporal também, que essas aquisições de dados são, às vezes, de décadas distintas, né? Mas é um desafio bacana e eu acho que o produto disso tudo vai ser um produto muito importante, não só para a engenharia costeira, mas também como pode gerar várias pesquisas, né, fundamentais para toda essa riqueza, né, que é a Amazônia. Obrigado, Jeffrey, foi ótima palestra.
Obrigado. Realmente, depois de todos os case studies, diz que esses aqui são os challenges, o desafio, mas não é o problema, que é a parte que temos que, ok, temos esse problema, vamos resolver.
Professor Carlos Young.
Esse esquema de modelagem, ela indica o que você tem que aprender. Como você vai fazer isso para você.
Carlos Young wants to ask a question.
Portuguese or English, whatever.
Whatever.
Yes.
Okay. Just to introduce myself, I'm actually, well, hello everybody. Hello, Rosman and Monica. I'm a professor at the UFRJ, but at economics, but working on environmental economics. But I also a collaborator of the State University of Mato Grosso, UNEMAT, and there we are involved in a long-term ecological program on the Paraguay River Basin. And we are not modeling with this level of sophistication the dynamics of water, but on the other hand, we are doing some research on carbon, and especially the interaction between vegetation and carbon in the river, in the Paraguay River. So it's not exactly a question, but I would like to invite you to give a similar talk and to have this connection, and of course all the Amazonas project as well, to connect you with what's going on in the Pantanal Basin, where this issue, when I was looking to the Aral Sea presentation and imagine what's happening now in Pantanal, the Paraguay River is getting lower and lower every year. And so it's just an invitation for you to give a similar talk and to have some exchange on what's going there.
Well, thank you. I'd be very interested in doing that. I mean, clearly, these are really important topics, and with all the problems going on in the world, and nothing's going to get better anytime soon, I'm afraid. But then the question is, what do we do? How do we adapt to it? The best information we can get and have responses to that is the strongest thing we can do. And the beauty of this stuff, what I always sort of kid about with the hydrology and rivers and water and so forth, all you have to know about water is that it goes downhill, right? It goes downhill at the same rate at the top of the Himalayas as in the Pantanal, as I'm on an island in the San Juan Islands now, as it goes off here into the ocean. And so long as you have those sort of common laws, and then how can you take what you've learned in one place and move to the other? And you saw in the examples I gave, from going literally from the Amazon to the Zambezi, same physical laws, and that gives you the strength to be able to take, gee, we've learned this here, let's go to the Pantanal. And the necessity is absolute. And I really have come to believe that if we can really dial in the thinking about the cyber infrastructure, the informatics component of this, makes life a lot easier.
Thank you very much. And Rosman, I mean, we need to have a talk with, I'm Monica's brother, so it's easy for me to have access to the, but this is a kind of very interesting interchange and possible application of results in a very different context, which has also some similarities.
I'd like to make a comment. Just congratulate you, Professor Jeffrey, for your lecture. Hello for everybody. I'm from the civil engineering program at Coppe, and we are working with water resource and environmental modeling and using hydrological models. And we have a joint cooperation with people from hydrological division of NASA. And we have a master thesis that was recently developed trying to approach different basins, the major basins in Brazil, and making a kind of water balance, simulating the components of the water balance at a 25-kilometer scale. And as I saw your presentation now at the end, your last slides, and this interaction with water, so I thought if there is a connection that we could make with your kind of work that you presented with CO2, because something that we are trying to work, integrate a little bit more the water resource balance and the biogeochemical cycles. So this is an interesting thought. Another curiosity, just about to hear from you, but is about China. You showed some areas from China, and I was curious about the big diversion project that they have there from the south of China to the north of China, because Beijing is facing a very water crisis. So do you have something to say about, comment on that? How do you look China in this framework? So,
no, interesting. I'm certainly very aware of the whole diversion north, south to north thing, and I've read a lot about, how well is it going to work or not. The Chinese are very skilled hydraulic engineers. That said, I mean, I don't really know enough about the specifics to really discuss very much. We've worked some together on some of the upper Mekong, the Langjiang areas, but that Northeast Brazil study, Northeast China, the 3H basin was my main connection. I've been invited to do other things and have done some on chemistry in the different areas, but not so much on that one, to be honest. But that country has serious water problems. And the whole Northeast, one of the things that really came out when we were doing that 3H basin study was trying to understand what the overall groundwater situation was. And not only is the groundwater being severely depleted, it's also becoming progressively toxic. I wouldn't drink any groundwater that came from there, frankly. But
okay. And what about the integration between the scales? Because you said you use the VIC with 5 kilometer scale, right? And
well, yeah, good question. I mean, so I think right, so backing up in time a bit. So Vic and some of the other models that came out at about that same time were really set up as sort of one leaf of 100 kilometers in scale kind of thing, to start representing the connection between the land surface and the atmosphere. Remember, it was only, 30 years ago or something that the atmospheric scientists thought that the land surface had nothing to do with energy water exchange with the atmosphere. Aeneas Salati from Sena was one of the first to really show that the evapotranspiration over the Amazon was about 50% of the precipitation. It was about that time that things really started to change. And so then Vic was originally 100 kilometers, then 25 and so forth. But Vic makes certain assumptions about the land surface that if you get much smaller than 5 kilometers, it really doesn't do it. Vic itself doesn't do this cell talks to this cell, talks to this cell. It basically says this amount of water leaves this pixel and goes through a convolution integral down here to some river gauge, imagined or otherwise. Then its neighbor does the same thing. They don't actually talk to each other. And those were the assumptions that had to be made with the computational power of the time, whereas something like DHSVM does. One cell goes to the next at a much higher resolution, but trying to get to bigger scales was really constrained by data and computer structure. But one of the things, I was just talking with somebody just a few days ago, so DHSVM can be a real nuisance to work with. And a lot of these things have all that legacy code. I mean, this whole business of generations of graduate students writing code and then leaving, and next one comes along as, what's this? And then we wasted a lot of time in those different projects, just trying to figure out legacy code and patch arounds and all that stuff. So now that DHSVM is being completely rewritten in Python, which I think is just wonderful. And that combined with new powers, computer powers and all that, I think will make a fundamental difference, because it's much more physically realistic than the Vic class of model is. I mean, that's nothing, Vic is great at what it does. But if you want to get down to, okay, let's what's going to happen at a local agricultural level or something, other than broad trends, it's not so great. So I think those are some of the exciting developments. That's something we really were pushing for when I even first, I'm not from the VIC or that modeling arena. I'm a river chemist, basically. But after getting understanding more about how these things, why don't we just rewrite this damn thing? Well, easier said than done. So I'm glad that some groups are really going to take that on. That'll make a huge difference. And combine that kind of re-level with the power of some of these new data sets, capabilities. Exciting.
Great, thank you very much. Let's keep in touch.
Yes. Thank you, Professor Jeffrey.
Para onde me achar, Mônica?
We have another question from Sarah Alves, one of our COPRI colleagues, and she's asking about the fluid mud is a problem for navigation in the Amazon rivers. How to improve the navigation using the modeling that you present? Is there any contribution for navigation also?
Okay, I will give that question to Mônica.
Right. I think she's a good one to answer to.
Yeah. But it's a real issue. So we do these transects from Macapá, and because we go across the river doing ADCP runs for 11, 12 hours to get the river flow change over the tidal cycle. And the channel in front of Macapá goes like this. I mean, it's a real, and you're absolutely right, that the navigation is a huge problem. In the middle of the channel, it can be 1 meter deep at low tide. So in the middle of an 11-kilometer wide channel, it's 1 meter deep. It makes no sense. So a ship really ought to stay where it's supposed to go. This issue of the fluid muds is, hopefully Monica will be able to model exactly where all those go, right? The school.
Oh, thank you. We have another question from Elinir. She's asking about, I was very integrated by the issue of data being too much for non-professional to handle. The big data combi, she said. I have experienced being unsure what to make of data myself. Is data modeling the main solution to this? How else do you simplify the data in your fields or ensure that your findings are understood?
Okay. So the question is, how much does, given how big the data is, how can we assure that it's, how to deal with it and how it's understood? Well, that's where the keeping on, well, let's think about that together on that. So you have to be able to process it cleanly. I mean, that's where all these data workflow things, I think, become really important. One of the points that in the summary slide was, if you have multiple data streams, they can actually, lots of people think, well, that just confuses life. It should help you constrain life. I guess I don't, you rephrase the question. I don't quite understand what the question itself is.
Yeah, sorry. I guess I was just asking, like how you make, in your field, how would you make this data and ensure that these models are accessible to like people that may not be familiar with it? I guess with regards to what you were talking about with the chain of knowledge, like how to get information to farmers and stuff like that.
Yeah, that's a really good, I mean, one of the things that we spent a lot of time in developing this stuff thinking about is, okay, so the basic engine is a pretty complicated chunk of software stuff. And ideally, that farmers or the non-specialist could log into their laptop and say, I want to know this or this condition. Okay, good. But are you really good? That person really good? So you've changed the boundary conditions and the input drivers say. Now, the problem from the practical point of view is that person going to rerun the whole model? And that, if so, I mean, that can get pretty complicated. It takes a while to run these things. Now, let's hopefully that the new generation of computing codes will greatly expedite that. One of the things that we have done a little bit in the past is say, okay, here are a set of pre-can conditions. So we run it for where input A is 5, input B is 7, and so forth. And say, okay, so here are a set of canned outcomes. And so I think there are various ways to get to there. An interesting, the first point you brought up was, how will people trust it? And that's a hard question. I mean, this is, and of course, given how science is being questioned around the world today anyway, that becomes even more challenging and important. But I think that the ability to get back, can you reproduce known properties? I mean, this back to our that river gauge in the side of the bank someplace. If it says it's the height is 78 centimeters and you can reproduce that, well, hard to argue. With the caveat that you can do that you can make a model say, get to that 78 several different ways. But there's a certain amount of buy-in that has to happen in this by the end users. But I think that's where some of this visualization stuff becomes really useful. Is if you can see, oh, okay, here's this blue cloud coming up over my town, then maybe you'll start believing it. But it's tough.
I have one last question from Professor Claudio Neves. I think if you want, Professor, you can ask your question directly. It's very quickly, and you can go on and give you the notes and the closing of the lecture.
Okay, thank you, Veronica. Jeffrey, thank you very much. It was a very interesting talk. And before I can you hear it? Hello, everyone. Good. It's okay. So thank you very much. And before I can say the closing remarks, I have just a brief question. You mentioned the problem of continuity. Students come and go, and then there is a problem with the continuity of the project. So, and that's the problem with long-term projects. One point is, what about the participation of the local residents, people who lived in near the rivers, and for the maintenance of the equipment that you have installed in Africa and in Asia? Did they participate? Do they keep the equipment? Did you have any problem with equipment being installed or damaged?
Fair question. I mean, that's certainly a concern. We've left very little equipment out. So the work in Africa took some samples, but it was not a long-term campaign. It was to go in and construct the modeling environment and so forth. We had a big campaign on the Mekong River that lasted some years, and I still have some involvement there. But all this, leaving equipment out is basically a bad idea, as you know. And so when sampling would typically be done by a team that goes out, put everything in the boat or wherever, go out and take everything home at night or the next day. I mean, sometimes you're running dial. But wait, that's not entirely.
And what about in US?
I just remember on that Tonley Sap Lake, we had several stations of leaving oxygen meters out for several days on end. But that would be done with local support watching over the equipment.
Mm-hmm. What about what do you do in US if you have to do a long-term project?
With equipment or people?
Do you have contribution of local equipment? Do you have voluntaries in US for taking care of the equipment?
So a broader question is, so this whole issue of citizen science has gotten much bigger. Starting off, I don't know, started with the bird watchers and so forth, but there are a lot of examples now, especially around the Pacific Northwest where I live, that of citizen groups who will take on equipment, watch after equipment. One of my colleagues, Rick Kyle, who's actually part of this project, who's director of the School of Oceanography, has done a lot of work across the Puget Sound region where he makes up, what we'll do is make up kits. Okay, take this bottle, unscrew the cap and go like that and put this cap back on and don't put your finger in it, sort of stuff. And he's had a lot of luck doing that kind of stuff. In our broader Amazon network, we definitely established local nuclei of investigators, but not with certainly weren't just people off the street, but at one point we even established a regional campus in Rondonia to do that sort of stuff. Recently I was involved with the Moore Foundation in trying to come up with low-cost sensors that citizens could just go out and use. But I think that there are.
I think that's might be.
So what?
Go ahead.
Yeah, it's the one of the
problems. No, okay, I think that's one thing that we might try to do here in Brazil. Getting the participation of the local citizens.
No, I think that's a
really
good idea. That an issue that we came up in the Moore Foundation stuff is great. So you can come up with sensors simple enough and rugged enough that people can do that. How do you relate those data to what the bigger picture is? So to me, you have to have a combination of, yes, this is a citizen scientist who's deploying this object, but then goes into a more sophisticated network that can actually ingest that information. So in this Moore Foundation thing wanted to establish spots around the Amazon, but the way they had it set up, ultimately, the information didn't actually go anywhere. So great. So we measured dissolved oxygen from stream. Well, if you don't know what the stream is doing overall, the information is not of much use. That said, you're starting to engage the people just so they start thinking more about the environment. So that's really good.
Okay, thanks, Jeffrey, and thank also to the audience. And I should say that Jeffrey, you are the third annual lecturer of our UFRJ COPRI. We had the first year, O for the ocean, that was Professor Thorsten Schlurmann from the Francis Institute, University of Hanover, and he talked about plastics in the ocean. Then the second talk was Dr. Conceição Joana Fortes from the National Laboratory in Civil Engineering from Portugal, and she talked about ports in Portugal. And so this year we had the R for rivers. And since you came here last year for the autumn school, you left a very nice, pleasant impression on all students and faculty at UFRJ. So I'm very glad that the students have chosen you for being the annual lecturer for R, the river. So next year we'll have C for coasts, and this is also the first time that is being broadcasted, and we should thank ASCE as Tom and Steve Balin and Sean for having this broadcast, and this talk will be probably recorded for ASCE. So thank you very much again, Jeffrey. And we have also the agreement of cooperation between UFRJ and the University of Washington. That was the first of the agreements that we have signed. So I guess now it has disappeared. You all have disappeared, but I can continue talking, I think.
Yeah,
so,
yeah, we can hear you.
And probably, okay, and probably we can go along and make some other type of cooperation and research between our two universities. So you are always welcome here. Hope to next year to have you here again, Jeffrey.
Well, thank you very much.
Okay, Veronica.
Certainly intend to be there.
Yeah, it's okay. As this year we are not in person, you usually give a thank you gift for the professor of the annual lecture. So as we're not in person, we made this picture just symbolizing you with our UFRJ COPRI totally. As thank you so much for being here today, for sharing your knowledge. Thank you everyone for participation in the discussion. Thank you, Professor, for being the professors for being here and the lecturer, everyone who spent this evening with us. So with no more information or no more things to say from us, I give you everyone good night. Thank you so much for being here.